So lesson 40, okay? Back to kind of this idea of units, right? In math, we always talk about units and how they're important because, for example, 3 feet is very different than 3 miles, okay? Cubic centimeters are very different than cubic meters. So the unit gives us some sort of idea of measurement to our number. Okay, it tells us how big that number actually is or how small that number actually is. Okay, so we're looking at units for the independent and dependent variables. Okay, so when we look at it that way, we spend a lot of time on this derivative, right? The idea of a derivative. So we can then look at the units on our derivative. Okay, so if I consider a graph of a volume, call it V of t, okay, like we have in our notes here. So the volume dependent on the time, okay, and it's got some sort of curve to it, right? Some value c is here. So we're looking at V of t. V is volume in cubic centimeters, and t is time in seconds. Okay, that's what we're looking at. So at time equals c, okay, which is here, the slope of the volume curve, right? So right here, we're talking about that slope of the tangent line again, okay? So here's our tangent line. Then the slope, here's our run and our rise, right? That's what slope is. So at time c, the slope of volume is equal to 1 cubic centimeter over 2 seconds, because the rise is the change in your y values, right? So the rise depends on the volume here, if we have the measurement of 1 and 2. And then the run is in time, okay? So that's the slope, and we've spent a lot of time on this. We know that the slope of a line is equal to the value of the derivative at that point. So volume prime at point C is equal to 1 cubic centimeter over 2 seconds. Okay? So we're assigning some units now to this idea of a derivative. So as we can see, the unit of a derivative is the unit of the dependent variable, so the vertical axis, divided by the unit of the independent variable, which is your horizontal axis. Okay, so we'll kind of put this up here. So generalize it for f at point x. So the derivative at x has the units of the vertical over the horizontal. Okay, because it's always rise over run, because derivative is the slope. All right, so that's what we're looking at. Still working on this derivative again, okay? So then if we ask ourselves to find the volume of a balloon at time t, and the volume is in cubic centimeters, and the time is in seconds, given by the equation of volume that depends on time is equal to 20 times e to the t power. So t is the time in seconds, and v is the volume in cubic centimeters. and we find it by this equation. So we want to find the rate of change of the volume when t is 3 seconds. Okay, well, start with our equation, right? We know that the volume depends on the time, and it's going to equal 20 times e to the t power. Well, rate of change, fancy way of saying slope. We know that the slope is the derivative. So we're going to find the derivative of our function. Okay, so find f prime of t, or v prime of t, sorry, not f. Okay, so we're finding the derivative of 20 e to the t, right? So multiplication, so it's the derivative of 20 e to the t with respect to t, right? So you pull out that constant, and then you take the derivative of e to the t. We know by shortcut, derivative of e to the t is e to the t. So the derivative of this function is the same as the original function. So v prime is equal to 20 e to the t. So we found the derivative, but then we want to find the rate of change when t is 3 seconds. Okay? So you find the derivative first, then evaluate the derivative at the time you're given. So it's 20e cubed. Okay? Units on the derivative are the vertical over the horizontal. So time is always our horizontal. So this is going to be centimeters cubed per second. We could use a calculator to figure out what 20 e to the third is. Okay, so you get that the rate of change of the volume is going to be 401.7107 cubic centimeters per second. Okay, so rate of change is slope. Slope is derivative. Find the derivative of your function and then evaluate it at your given value, right? So for this problem is 3. And then the only difference now is you're assigning units to it, right? So we knew it was a slope, but now we can visualize this as, we said it was a balloon, right? So how big the balloon is, depending upon how long the balloon has been blowing up, okay? So this is changing at about 401 cubic centimeters per second. Okay, it gives us an idea of how big the balloon is getting, how fast big it's getting depending on its time. Okay, so assign units to our derivative now, because derivative is slope and slope is rate of change. Okay. One other thing to mention is velocity and acceleration. Okay. Acceleration is a fancy way of saying the rate of change of the velocity. So if you have a velocity function, which comes from the speed of something, then you take its derivative to get the acceleration. All right. So units on derivatives. Okay. Then the next thing in lesson 40 is something called the normal line. Okay, so usually when you hear the word normal, people think it means like ordinary, okay? Not the case for math. So when we say the word normal in math, we are talking about perpendicular. Okay. It goes back to like Romans and Latin words and all of that. So a carpenter's square is called a norma. So we use normal to say perpendicular. Okay? So if we're asked to write the equation of a normal line, you're being asked to write the equation of a line perpendicular. Because normal means perpendicular for us, okay? So we know that perpendicular lines have opposite reciprocal slopes. Okay? So if you get an equation and you're asked to write the equation of a normal line, the first thing you want to do is take the curve, and then you're going to find the slope of the curve, and then use that to give, or the slope of the tangent line. So you take the derivative, find the slope, then the normal line is going to have an opposite reciprocal of that. Okay? And then you just have to find the point of intersection between the line and the curve, and you do that by using your x value. Okay? So looking at our example, our graph is defined as y equals -3 times the natural log of x, and you want to write the normal at the equation of the normal line at x equals -3. Okay? So the very first thing you need to do is you're going to find the slope of your tangent line. And the slope of the tangent line at -3 is the derivative evaluated at -3. So we're going to find y prime. So take the derivative with respect to x of -3 times the natural log of x. The -3 comes out. The derivative of natural log is 1 over x. So we get -3 over x as the derivative of -3 times the natural log of x. Then you're going to take this and evaluate it at x equals 3. So we get -3 over -3, which equals 1. So that is the slope of the tangent line. Okay? So the slope of the normal line has an opposite reciprocal. So the normal slope has to be perpendicular. So opposite reciprocal of 1 is -1. Okay, then the equation of a line is y minus y1 equals slope times x minus x1. So we know the slope of our normal is -1, and then you just need to find the point that the line is passing through. Okay, well, you're going to do, when x equals -3, what is y in your original equation? So you get y equals -3 times the natural log of -3. Or the absolute value of -3. Using our calculator, okay? So, because it says the absolute value of -3 in your equation here, right? So that simplifies to, you have the point -3 natural log of 1 over 27. I just evaluated the function at x equals -3. So then this is your x1, y1 for your line. So we get y minus the natural log of 1 over 27. Just using properties of logs to simplify that. Equals -1 times x minus -3. Okay, and then just simplify. I'm fine with you leaving it in terms of natural log. Okay, so this is y minus natural log of 1 over 27 equals -x minus 3, and then solve for y. So y equals -x minus 3 plus the natural log of 1 over 27, which would be the equation of your normal line. Okay, so normal lines are perpendicular to tangent lines. So we know the slope of a tangent is the derivative of the function evaluated at the x value. Okay. All right. So those are our normal lines. The last little thing we go over in this lesson is maximum and minimums on your graphing calculator. Okay, so you could do the derivative and finding your critical numbers. You can also use your calculator to simply graph it, and then you can clearly see, right? If we look at our book, lesson 40 here, right? So I graphed a function. This is sine x, okay? That's what it looks like. You can see maximum and minimums on there, right? So I can use the trace function to calculate your maximum and minimums. You can move it along the graph, right? Here's a maximum, a minimum, and it's going to give you an approximate. It happens at y equals 1, right? We know that sine has a maximum of 1, and it's about 1.5, 1.6, okay? So instead of finding the derivative. So graph your function, look at the interval, and then locate on the calculator the maximum and minimums.